The pinwheel is an emergent property of the interactions between puppies, whose only rule is to try and keep access to the milk, and therefore to push in a random direction. So it's all about finding the simple rules from which complexity emerges. I call this simplifying complexity, and it's what we do at the Chair of Systems Design at ETH Zurich. We collect data on animal populations, analyze complex patterns, try to explain them. It requires physicists to work with biologists, with mathematicians and computer scientists, and it is their interaction that produces cross-boundary competence to solve these problems. So again, the whole is greater than the sum of the parts. In a way, collaboration is another example of complex system. And you may be asking yourself which side I'm on, biology or physics. In fact, it's a little different. And to explain, I need to tell you a short story about myself. When I was a child, I loved to build stuff, to create complicated machines. So I set out to study electrical engineering and robotics. And my end of studies project was about building a robot called ER1, looked like this, that would collect information from its environment and proceed to follow a white line on the ground. It was very, very complicated, but it worked beautifully in our test room. And on demo day, professors had assembled to grade the project, so we took ER1 to the evaluation room. Turned out the light in that room was slightly different. The robot's vision system got confused. At the first bend in the line, it left its course and crashed into a wall. We had spent weeks building it, and all it took to destroy it was a subtle change in the color of the light in the room. That's when I realized that the more complicated you make a machine, the more likely that it will fail due to something absolutely unexpected. And I decided that, in fact, I didn't really want to create complicated stuff. I wanted to understand complexity, the complexity of the world around us, and especially in the animal kingdom. Which brings us to bats. Beerschen's bats are a common species of European bats. They are very social animals. Mostly they roost or sleep together. And they live in maternity colonies, which means that every spring the females meet after the winter hibernation, and they stay together for about 6 months to rear their young. And they all carry a very small chip, which means that every time one of them enters one of these specially equipped bat boxes, we know where she is. And more importantly, we know with whom she is. So I study roosting associations in bats. And this is what it looks like. During the day, the bats roost in a number of subgroups in different boxes. It could be that on one day, the colony is split between 2 boxes. But on another day, it could be together in a single box, or split between 3 or more boxes. And that all seems rather erratic, really. It's called fission-fusion dynamics, the property for an animal group of regularly splitting and merging into different subgroups. So what we do is take all these data from all these different days and pool them together to extract a long-term association pattern by applying techniques of network analysis to get a complete picture of the social structure of the colony. Okay? So that's what this picture looks like. In this network, all the circles are nodes, individual bats. And the lines between them are social bonds, associations between individuals. Turns out this is a very interesting picture. This bat colony is organized in 2 different communities, which cannot be predicted from the daily fission-fusion dynamics. We call them cryptic social units. Even more interesting, in fact, every year, around October, the colony is